Welcome back. We are in the fourth session right now. We did a 50-something minute session this morning. We're back at it for another 50-minute session. We're going to finish up unsigned integers. We have just figured out how to represent unsigned integers as decimal digits and binary digits. Can somebody guess what the next stage is going to be? If I know how to represent them as decimal, and I know how to represent them as binary, we've just learned how to go from binary to decimal, right? If I give you a binary representation, you can use the power representation of that thing to turn it into decimal. What might be a natural question that comes up from that? Yeah, if I know how to go from binary to decimal, I might also want to know how to go from decimal to binary. So recall if n is a unsigned integer, then we can write n. Can somebody use the sentence that I would like to use here? You were not only close, I would say you were spot on. What's this thing called? How many? N plus 1 decimal digit representation. So that's one representation. What's the other one? So you use the word mango or November. November is for N and mango is for M. Mango. Awesome, Ethan. B sub M, Bm minus 1, all the way down to, sugar. B2, B1, B0, sub 2. Could you guess what we call that thing? M plus 1 Yeah, you're correct. Binary digit. We earn the right to be lazy, right? Yeah. Just to go a little nonlinear, what were the three radix values that we were going to use? 10 to 16. That's really awesome, Michelle. When I grow up, I think I want to be like Michelle. I just have to grow up first. I have this feeling you got your stuff together. So radix 10. This is what we're going to call radix 2. And then I actually don't know if I use this notation. Kind of confused at what I wrote for myself there. I don't even know if I got that far, to be honest with you, when I wrote these notes. Could you guess what we might say for hexadecimal? H sub L minus 1, H2, H1, H0. Instead of base 10 or base 2, we would call it base 16. In this case, we would call the entire thing radix 16. What would we say about that representation? Yeah, this is going to be the L plus 1. I think it's hex E, right? I don't think it's hexa. How do you spell it? Hexa. Is it hexa? Stupid English. Make a decision, English. I want English to be a function, not a yeah. Okay, so right now to convert from binary to decimal, we know that if we write n equal to b sub m minus 1, all the way down to b2, b1, b0, how would I get the corresponding binary representation of that sucker? Excuse me, decimal representation of that sucker? Literally, just take whatever the binary digit is. Each binary digit is either of value what? 0 or 1. So match each digit with its corresponding power of 2 and be done with it, right? Okay, so that is our mechanism by which we can convert from binary to decimal. And then, as Kaio was so eloquently saying, we might ask ourselves, how do we convert from decimal to binary? There is a very eloquent one. This is only, you're probably familiar with the fact that I've said this 50 times. I've only taught this two times, and so I haven't really figured out the best way to introduce this. One thing we might do is to look at an example. And I don't know if we want to do... How do you all feel? Would you rather have me track the examples that I have in my notes, or do new examples so that you have a more variety? New ones. Okay, that's cool with me. So that's called democracy by one. All right, so let's take a look at an example. Let's let n be equal to, give me your favorite 2-bit binary number that is odd. Decimal number that's odd. Gotta be an unsigned natural integer.
Okay.
Unsigned integer. 17? I wanted a 2-bit is what I was saying. 2 digits, sorry. You got it. Okay. So one really, really easy way to do this, find the biggest power of 2 that's less than this. So what's the biggest power of 2 that's less than 17? 16. Subtract 16 from 17 and I'm left with 1. So this one's not too bad. So another way to write this is that it's 2 to the 4 plus 2 to the 0. What's another way to write 2 to the 4 plus 2 to the 0? Well, that's 1 times 2 to the 4 plus 0 times 2 to the 3 plus 0 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. Ugh. Which is what? 1, 0, 0, 0, 1 base 2. Let's do something much harder than 17. So give me a 2-bit number. Don't make it too easy for me. 97, that sounds much better.
You're saying 2-bit number?
2-bit decimal number. 2-dit. Don't call me a dit. I'm not a dit. I'm a dit. There's a difference. Yeah. So what did you say that was? 97?
Yeah.
This one's much harder, right? Why is this one much harder? So let's go ahead and do this. Give me the biggest power of 2 that is less than 97. And then I might actually say this. How many of you have memorized powers of 2? Me too. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192. Yeah. Yeah, so the thing that I'll say, this table, I provide this to your notes. I have the first 14 things, 13 of those memorized without thinking about it. Ask me why I would do that. Because eventually it's easier to memorize than to look up. If you work in this long enough, it's better to have stuff in your brain than to have to like get up out of your chair, go over to where your notes are, take your notes out, flip to the page, right? The other thing that I have never really seen, and I did this in this table, was large powers of 2. I had a dream when I was a younger man that I would have every one of these memorized off the top of my head. And then I like had to do stuff with my life. It's there for you. There, I actually wanted to fill out this table. At some point I'll update this with 2 to the 53, 2 to the 54, and then also 2 to the 63 and 2 to the 64, just as a string of digits. This table took me about 40 minutes to make in Excel. I'm not claiming that you should memorize this. I'm also not claiming you should make this for yourself, but I do want to say that if you wanted these powers, they're there for you in that. The reason that I say this is, let's take a look at 97. So what's the biggest power of 2 less than 97? Okay, so let's go ahead and do this. 64. What happens when I take 64 away from 97? Say it again?
You get 33.
33. Yeah, this one's even still too easy, huh? It was a good try, though. So what would that be? Okay, so let's go real slow on that one. 64 is... This one makes me really smile because I get it for free. If I know that 64 is a power of 2 and I'm looking for the base, the power, it's literally the first digit in that number, right? Okay. So this is 2 to the 6 plus 2 to the 5th plus 2 to the 0, which is 1 times 2 to the 6 plus 1 times 2 to the 5th plus 0 times 2 to the 4th plus dot, 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 plus 0 times 2 to the 1st plus 1 times 2 to the 0. What's the minimal number of binary digits that I need to store this number? Thank you so much, Kenny. I wanted somebody to say 6, because making mistakes is a great way to learn. Why did you say 7?
You have to account for the 0.
Yeah, you got to account for the ones bit, right? So in this case, I would have 1, 1, 1, 2, 3, 4, 1. Do you notice that this process can be really painful? Why would this process cause a lot of pain? What do you have to do every time that you do this process?
You figure out a power of 2.
Yeah. In particular, where does this algorithm start? Does this algorithm start with the most significant bit or the least significant bit? Yeah, so this algorithm would work. It's just a slow algorithm, right? Let's look at an equivalent algorithm. What I mean is an algorithm that allows us to produce the same information in a different way. So let's do, this was what we call the naive algorithm. And naive just means I couldn't do this on a timed test and solve all the problems. I don't know if I've told you this. You will have no time constraints on any test in this class. Time is not going to be an issue. If you need more time, you stay. Okay? I never want time to be an issue. I also don't want notes to be an issue. If you need 12 pages of notes, you use 12 pages of notes. If you want to take 4 hours on a test, take 4 hours on a test. I will not stay until 11 p.m. because my kids and my wife are waiting for me usually after work. But however much time you need to take your test, you take it. It's not about being fast. It's about representing accurately what you have. Okay, so what I want to do, we're going to talk about an algorithm which has to do with division. So we're going to look at step numbers. We'll have what we call a division. And then we'll have integer quotient. We might call this the integer part of the quotient. And then we'll have what we call a remainder. Someday I will be able to do this really intuitively, like where does this come from? The more I teach, the less I suck. So I'm close to my maximum suckage at this exact moment. Not funny? I thought that was hilarious. All right. 97 divided by 2. What is 97 divided by 2? Well, 100 divided by 2 would be 50. So it's, yeah, it must be something like 43 probably, 43.5? 48, yeah. 48.5. And let's think about 48.5 as 48 plus 0.5. And let's think about that as 48 plus 1 over 2. Shall we? So what is the integer part of that quotient? So this is what we would call the integer part of the quotient. What's the remainder? The numerical remainder. I would say it's 1. Remainder 1 mod 2, right? So this is kind of funny. This equal sign is not the equal sign that you're used to. Right? Because I'm not asking what is the numerical value of 97 over 2. What am I asking? What is the integer part of the numerical value of 97 over 2? And then I'm also tracking what we call the remainder. So that's step 1. Can you guess what the next thing we're going to do is? We're going to take this number. Yeah, so step 0 was just to take the entire number, drop it into the numerator in step 1. Okay, can you guess what step 2 is going to do? Take the integer part of the remainder, or the quotient, divide by 2. What is the output of 48 over 2? 24.0. Today is Wednesday, right? So it must be 24.0. What is 24.0? Well, it's 24 plus 0 over 2. What's the integer part of that remainder? No, sorry, of that quotient? 24. What's the remainder? 0. Anybody see a bit string? Okay, so let's think about this. The 0th step was just to say that the number in base 10 that I'm looking at is 97. To start the first step, what did I do with 97? I dropped it in the numerator, divided it into 2. I was looking for an equality. What specific thing was I was looking in that equality? The integer part of the quotient. So I track the integer part of the quotient, and then the remainder, what's left over, I track as a separate bit, right? To go on to the next step, what do? Take the integer part from the step before it, put it in the numerator, divide by 2. Could you guess what step 3 starts with? So 24 divided by 2. Well, let's see. Today is Wednesday. 24 divided by 2 probably should be 12.0, which is 12 plus 0 over 2, which means the integer part is 12. What's the remainder? 0. What's the next step there? 12 divided by 2. What's 12 divided by 2? 6.0, which is the same thing as saying 6 plus 0 divided by 2, which is the same thing as saying 6 with a remainder 0. Does anybody see the pattern? The first algorithm that we suggested started with the most significant bit. Can you guess what this one does? Least significant bit. 6 divided by 2. 3.0. Another way to say 3.0, which is integer part 3, remainder 0. Step 6 of this algorithm. Could you guess how many steps there's going to be? The number of bits. So this is 1 plus 1 over 2. Integer part is 1, remainder is 1. So I take the integer part, 1 over 2. This is 0.5. Integer part is 0. Remainder is 1/2. I have 0, 1. Can I do any more work? My work is done here. 1, 1, 0, 0, 0, 0, 1. How many zeros did I have after those first two ones? I'm not claiming that one is better than the other. In fact, I don't know which one is better. This one does not require you to know the powers of 2. The other one required us to know the powers of 2 and to be able to subtract, right? Which one does this require? What does this require? That you know how to divide by 2 and also split them into integer parts and remainders, right? So that's a fast way to do that calculation quickly. Are there questions? I'm sure there are questions. The question is not, are there questions? The question is, how do I capture those questions? I'm going to let you play with, so maybe I'll let you do this actually. See if you can, so I'll have you reconfirm what we've done in the notes. So this is going to be example 3.12. So use the second algorithm that we just did to find the binary representation of n equal to 145 sub 10. What would be fun is if you did both of them, but one of them is fine too. Anybody finish that? Okay. If you finish that, please write for yourself the general theoretic hexadecimal representation along with its binary, its decimal conversion algorithm. So we've had this. If you haven't finished that, don't listen to me, okay? This is the bad part of having 40 people in one class. The class is useful for no one person. How many of you have finished the example calculation? How many of you are still working? You're still working, keep going. If you're not still working, could you read it to me? All together now. One. How many zeros? 2 zeros? One followed by 2 0, 1 followed by 3 0. 1 1? All right. So check yourself. If you haven't finished, check yourself. All right, so here we go. We have these 3 different representations. We've got what we call a decimal representation. This decimal representation, numerically in terms of a power structure, looks like this, right? So each decimal digit times its corresponding power of 10, where the index on the digit represents the position, represents the power. Binary representation, each binary digit, each bit, is correlated, the index of the bit correlates with the power of 2 on that bit. What would that immediately mean about hexadecimal representation? Well, so let's go real slow. Each hexadecimal bit, each hexadecimal digit gets assigned what? 16 to the ith power. So let's think about this for a minute. The number n, which is 1, 4, 5 in base 10, we just found out that that was going to be 1, 0, 0, 1, 0, 0, 0, 1. When I see that string, one of the first things that I think about is powers of 2. The binary representation of this sucker, well, I'm going to have 1 times 2 to the 7th plus 6, 5, 4, 1 times 2 to the 4 plus 1 times 2 to the 0. So if I start at 0, 0, 1, 2, 3, 4, 5, 6, 7, literally each digit, each bit is either give me a power of 2 that size or don't give me a power of 2 that size. Right? So now the question is, how would I convert that into hex? So let's do something real quick. 16 to the 0 is 1. 16 to the first is 16. 16 to the second is going to be 2 to the fourth to the second, which is 2 to the eighth. How many hex digits do I need to represent this number? Here's a better way to say it. So let's do a quick question. What's the largest possible number I can get using 8 binary digits? Let's call it capital M for max, right? Go ahead, James.
1, 1, 1, 1.
What is that?
Add that.
1 times 2 to the 7th plus 1 times 2 to the 6th plus 1 times 2 to the 5th plus plus 2 to the first times 1 times 2 to the 0. What's another way to say that? 127 plus, sorry, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. Okay. Well, we're not really sure. That's a big set of numbers, isn't it? Let's do something. Let's see if we can make some conjectures here. You know what a mathematician does when she sees a problem that she's never solved before and it looks really hard? She says, well, screw the problem I'm working on. Let me solve an easier problem. 1 plus 2 is 3. 1 plus 2 plus 4. 7. 1 plus 2 plus 4 plus 8. Just take the one before it and add the next power of 2. 15. 1 plus 2 plus 4 plus 8 plus 16. Okay, are we ready for a conjecture yet? I almost want to go to Misha since he's had to suffer through me for so many hours of his life. That suffering should be worth something, right? Yeah, go ahead. What's the pattern you notice? That's called the Tower of Hanoi. And yes, you better believe that my 1 and 3-year-old have played with that for many hours. They don't know it, but they are already math nerds. Okay, so think about this for a minute. If I take 2 to the 5th plus 2 to the 4th plus 2 to the 3rd plus 2 squared plus 2 to the 1 plus 2 to the 0, what number do I get? 2 to the 6 minus 1. Could you guess if I took 2 to the 6th plus 2 to the 5th plus 2 to the 4th plus 2 to the 3rd plus 2 to the 2nd plus 2 to the 1 plus 2 to the 0, what number I would get? This is called a proof by induction. You want me to do that proof? How about I let you do that proof? Well, all computer scientists are mathematicians. Not all mathematicians are computer scientists. What does that immediately mean about the number 1111111 base 2? Try again. This must be 2 to the 8th minus 1. Well, 2 to the 8th, I suppose that's going to be something like 256, right? What's the largest possible number that I can represent with a string of 8 bits? 255. When we get back to this problem, the problem here was to take the number 145 and represent it as a hexadecimal number, right? The largest hexadecimal number with 2 bits, what's the largest hexadecimal number with 2 bits? FF, right? So the question is, when I'm thinking about the number 145, what power of 16, what thing can I multiply by 16 to get slightly lower than that number? Or perhaps our same algorithm works again. What did we do in the algorithm associated with powers of 2? Yeah, so would you guess instead of dividing by 2 what we might do? So 145 divided by 16. Anybody know what that is? (145) divided by 16, 9.065, which is 9 plus 0.065. What is 0.065? 25, sorry. Yeah, it's 1/16th, right? So this is 9 plus 1 over 16, which means the integer part is 9 and the remainder is 1. So this is 9, remainder 1. What did we do for the next part? Yeah, so we take this thing, we divide by 16. This would be 0. Well, it doesn't really matter what the rest of it is. We already know what it is, right? So this is 0, remainder 9. So what's the hexadecimal representation of this number? Nine times 16 to the 1 plus 1 times 16 to the 0, which must be 91. Let's go ahead and check that so that you know that I'm not smoking anything, or if I am, that it's really good stuff, right? I'm definitely smoking something. Which is crazy because now you have an algorithm to convert between any basis and decimal, right? Okay. So, now the claim we can do some work. Should we go over to Matlab? We're going to go till 12 and take a break and come back. Let's go to Matlab. Okay, so check this out. How many digits did I need let's undock this sucker. And then we'll minimize that. Okay, check this out. So let's CLC and let's clear. Okay, let's do bin to, oh, excuse me, des to bin. Can you guess what des to bin means? Okay, so let's take 145 and convert 145 to binary. Ready? Oh, that was scary. Okay, let's do something else. So I'm going to format hex. Could you guess what format hex does? Okay. Uint 8 of 145. What do I expect? What does that tell me? When MATLAB returns 91, what does that tell me about the value placed in the string of memory bits in the depth, deep down inside the computer? What are the string of memory bits? And do not tell me 0 and 1s, tell me lows and highs. And let's start with the biggest, most significant bit first. High, low, low, high, low, 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 high. Which means hexadecimal is an encoding of voltages. Right? Tell me this. What is the absolute largest number that could be encoded in Uint 8? Say it again. Try again. Yeah. No, don't be sorry. The more mistakes we make and correct, the smarter we are.
256 numbers can be stored.
Yeah, that's right.
Number is 200.
What does that mean, FF? F means, so now I got to do format long. F means 15, right? How would I break Uint 8? Now the question is, well, what would happen if MATLAB tried to store 256? Do you know what we call that in numerical computation? Overflow. Let's see what happens. What does MATLAB do when it has an overflow number? It maxes out that data class, and I can tell that that's overflow because if I did des to bin 256, how many bits do I actually need? 9. Because I need a power of 2 to the 8, right? But that's not what FF represents. Welcome to numerical computation. Check this out. This is why I want you to understand what the hell is happening underneath, because if you don't understand this, you will not understand this line of code. 256 minus 255, what is it?
1.
No, it's not. It's 0. That's what MATLAB's telling me. The 256 minus 255, MATLAB has just claimed that that number is 0. If you do not understand the theory behind this and you just trust MATLAB, you can produce numerical nonsense and you will say, this nonsense is true because MATLAB has told me so. But now, as users, you are empowered, and you will continue to be empowered the entire class to say, MATLAB is speaking bullshit because, why is MATLAB speaking bullshit in this case? What would I immediately do? What's a super easy way to fix this problem? Yeah, except that MATLAB doesn't give me an extra bit, right? Use a different native data class syntax matters a little. It does. Syntax is at the control of the mind of the coder. If the mind of the coder understands the language, then the language is the servant of that programmer. If the mind of the coder does not understand the language, then the programmer is the servant of the language. Do you know which of those I would want you to be? Let me not say what I want you to be. Which of those am I designing my class to help my students become? Yeah. I want you to see that now because this is a very different look at it. I've never seen a teacher teach like this. It's why I became a teacher, so I could change the stupid stuff that I saw. Right? And then I'll shut up.
Specific question. Would it not be useful to spit an error message when you overload the data class, or does Matlab trust that if you're using that class, then you know what the
Well, you tell me.
Because if in your program you go and overload your data class.
What would Jeff Anderson say if you were writing MATLAB for me?
Go ahead and look up doc.
No. I would say the opposite. Think about how I made you do documentation. Did I let you be lazy and put the documentation burden on the reader? Think about how I had you comment your code.
Scrutinizing everything.
My feeling is you got to make it as easy as possible for your readers. However, you just did your first numerical experiment that let you think, that let you see something about the coders at MATLAB. What I wouldn't call it, I mean, yeah, they earn the right to be lazy, but what's the attitude that they have? Did they produce an error message? What attitude do they have? If you use this language, you should know what you're doing. And if you don't, not our problem. I say shame on them, but let's forgive them immediately. Computers have only been around since the 1950s. Probably these people want to feed their wife or family and kids and put a roof over their head. And so they solve one problem but not the other one, right? We'll talk more about that. But yeah, I think that's a really easy way to fix this. You have overflowed. Is that what you meant?
Yeah. Because if you have something in your code where it tries to store a value unintentionally, like the user puts in an input you don't expect, it overloads the class and the whole.
So what does that tell you when you're working with numerical data?
You gotta be careful about how you store it.
The data class that you store it in fundamentally changes the way that you represent that in memory. If you choose an inappropriate data class, that might do what?
Break the code.
Cause errors that the uninitiated user will be blind to, but will fundamentally change the way that those numbers are represented. It is now 11:57. I would like to take a break. We are pretty much done. There are some last little things that we'll clean up next time we see each other. When we come back at 12, probably 12:10, we'll talk about Lab 2. You know what? I'm going to do this now on camera, just so you can see this. And then I'm going to go make some copies. I went to bed at 7. Okay, let me say this. I woke up at 2:15 this morning. Started working at 2:30 after I got my cup of coffee. And I worked continuously until my younger son woke up. Applied linear algebra at 6:45, so I got some good work in. 4 hours and 15 minutes of continuous work without break, which was awesome. Here's what I did. The old Lab 3 prompt is gone. You can't even download it because I won't use it again. I made 2 videos. One video is from a few years ago, but it's never been seen in public before. So you might think, some of you that follow my channel might think you've seen this video before. You have not. 2 years ago when I was filming this, I realized that I wanted to get to a space in my MATLAB class that I would use this. So this video gives you an introduction to a paper that I published 2 years ago with a guy named Mike McCusker. I give free access to that paper online. You don't have to worry about any of that. The second video is fresh this morning. That 8 minutes took me about 3 hours of filming. And you'll see up on the top right-hand corner, you can see a timestamp of when I was working. Yeah, you're right. So there's been a few people that read this. So today, what I'm gonna go make some copies for you. When I was doing this, the other thing that I did in addition to filming the videos, do you know why I tell you about how much I work here? Because I want you to feel respected. It would be a lot easier for me to use other people's resources, but I think it would be a worse course. Do you remember when I don't know if I've said this, that I bleed for you? Assuming that I will not get divorced and that I won't die, you have a half of my bandwidth. When I tell you these things, I want you to know. You ever have a teacher that pushes you really hard, but it doesn't look like they're working that hard? I had a lot of those teachers. They gave me really, really hard assignments, and they were always bright-eyed and bushy-tailed, and it didn't look like they put that much into their classes. That's not me. We bleed together. It is very often that I bleed a little bit more than you do, but I am getting paid for this, right? It is very often that I put more hours into a class than the top student in that class. So just know when you're suffering and this class is hard and you're working and you're like, fuck, this is taking a long time. I feel the same way. You deserve every minute I can give you, and you deserve every minute you can give you. You want to know what my opinion of a genius is? A hard worker that solves problems that most people don't even know are problems years before other people realize it and stays at it for decades. That's a genius. Every single one of you is genius. I'm going to model the type of work ethic that I know you all have in you. So, today, the job of today, and I think this will be enough for at least the next work process. The last thing I'll say is you will succeed in my class. You're going to do great in this class. Every quarter, my students astound me. If you have problems meeting deadlines, don't trip, come talk to me. If you have personal emergencies that come up and you need accommodations, come talk to me. What are my 2 rules about what I'm willing to give my students? What are the 2 things I'm not going to break ever? Never going to get a divorce, and I'm not going to die. Like, she can divorce me. That's her choice, right? But I'm with her for the rest of my life. Right? So if you put me in a position, if you miss a bunch of stuff and you're putting me in a position where I can't grade your stuff at the end of the quarter, I'm going to tell you that. I'm straight like, you're putting me behind here, right? But if you have stuff that comes up and you need accommodations or you need to change something, just come talk with me. Just speak with me individually. I don't know when the next time I'm going to touch Lab 3 is. I imagine it's going to be tomorrow at 3 a.m. or 4 a.m. whenever I wake up, so I can get this done sooner rather than later. Your Lab 3 is going to consist of some reading. Do you remember in the last set of reading that we did, some of the readings were you would read it and then create a cheat sheet? I actually have not finished reading all of these deeply. So I did a ton of, about 4 hours last time I did this class and another 2.5 this morning to find the best possible articles that I could find for you. I had this major question for you in Lab 2, right? Do you remember what my question is? Why do we care about Matlab? And to be honest with you, I don't care that you become proficient in Matlab. I'm paid to teach you some fundamentals in Matlab. I do care that if you plan to be a professional scientist, that you know how to use computers. That I care about really deeply. If Matlab is the form with which you do that, great. Matlab is a symptom of a much larger process, which is computers have become fundamental in science. Our education system is completely and utterly useless. We teach you solutions to problems that were solved in the 16th and 17th century, and then we say those solutions are going to equip you to solve problems of the 21st century. Right? If somehow you solve solutions of the past, We're going to teach you to solve problems that the experts sitting in front of you don't even know how to solve. That's dumb. Part of the issue in this class is you are learning scientific computing. Scientific computing really didn't come into a field as such until the 1960s or 70s, and it's only been around for about 40 years. Do you know how long it takes to change curriculum? We measure classes on the order of hours, right? Do you know how fast I would measure curriculum changes in academia? Centuries. That's not funny to any of you. That's funny to me, right? Yeah, it's sad. Part of my job this quarter and part of Lab 3 will be to get you familiar with the landscape in which Matlab exists, and more importantly, start helping you answer the question, how can I make money? How can I make a career using a computer? I will email you when I have this updated. I'm going to go make copies of the readings so that you don't have to print those out if you don't want. I'll ask any of you, I'll ask in a second. So I will be asking every single one of you and myself, it's not just you, to read 5 documents. Can you guess which ones those are for Lab 3? This is a 3-pager, that's a 3-pager, that's a 1-pager, that's a 3-pager, that's a 7-pager. This 7-page document is the most difficult out of all of them. I will read every word of these documents with you. I also plan to, for each of these documents, I plan to give you a 1-page reflection that you will read and then fill out the reflection with some definitions that you write in your own handwriting, reflection questions that I asked you to do, and then the thing that you'll submit to me, could you guess? The reflections. This one, in addition to a reflection, you're going to submit a cheat sheet. One of my hopes is to give you an unfair advantage. And you'll see this as we talk. Do you know the best type of fights I'd like my students to be in? The ones that you win. When I'm not claiming that you're going to go on and get a job in science, but when you do, you might submit your resume with 700 other, or 400, or 40, or 10 other people, right? My hope is that I can be part of your team that gives you an unfair advantage, if you wanted it, to get that. And one thing that I would say is scientific computation, you're going to see, I highlight some problems. A lot of people don't know a lot about this field, myself included. It's a young field. There's a lot of good work to be done here. I'm going to go step out and make copies. Today's lab, you can get introduced. A second problem in lab today, you all will be teaching yourself how to load data into Matlab and how to produce plots. That's not the reading problem, right? Like, why do I care about Matlab? How do I see this in my future? Every lab I plan to give you, why do I care about Matlab? How do I see this in my future? The last one was your academic plan. This one's going to be some reading, right? I also plan to give you what I would call a scientific computation problem, right? The last scientific computation problem was a mortgage problem. This one's going to be a pendulum problem. While I'm gone, one thing that each of you could do is to watch each video in the playlist fully, right? If you finish those videos and you wanted to start reading, you could start at the top and work your way down. I would be absolutely amazed if somebody in this class could watch these videos, read all of these documents, and understand that content before I get back from copying. Yeah, well, yeah, okay, other than him. Any questions for me? I'm sure there are tons. I have a bunch of questions for me, like what do the first 2 documents say?
So we need to make a reflection for 1 till 4 and then
I will update, yeah, so right now all you need to do is just watch those videos and maybe start the first document. I will have reflection prompts for you ready. As soon as I have those, I'll upload them, send it out. I'll also have a lab prompt. But for today, in this class, watch the 2 videos, start the first article.
And the cheat sheet is for number 5?
The cheat sheet will be for number 5, yeah. Can I go make some copies? All right, I'll be back. Thank you so much for your patience with me. Someday I'm going to be good.
What is good?
Not bad.